Hello, everyone, and welcome to the show. This is the Geek Narrator podcast. I am your host, Kaivalya Apte, and today I have Simon with me, and he's coming back on the show. Last time we talked about how you can think about building a database on top of object storage, and which was an interesting idea. We had a lot of interesting discussions around it. And today we are going to talk about all things vector, like vector search, vector databases, and we'll try to understand from Simon's experience and how to think about it, how to build a mental model to solve and build applications using vector search and vector databases. So, welcome, Simon. I'm really excited to have you back on the show. For our viewers who are new to the channel, who are new to listening to you and new to TurboPuffer, let's start with a bit of introduction about yourself, about TurboPuffer, and what you have been doing these days.
Yeah, absolutely. Yeah, my name is Simon. Thank you so much for having me on the show again and to be back. And last time we talked about building a generic database on top of object storage, and I think today we'll get into TurboPuffer and building a search engine generically on top of object storage. You asked for a little bit of the origin story of I guess the database and myself. So I spent almost just shy of a decade building infrastructure at Shopify. Although I saw the rise there from hundreds of requests per second into up to 1 million. And as part of that, worked on almost every single part of the infrastructure, including search. And when I left Shopify in 2021, and I spent a little bit of time kind of hopping between my friends' companies and consulting on infrastructure, vesting a little bit of equity in their companies and helping them out with something that was top of mind. And for one of the companies, the biggest thing I did for a lot of these companies was tune Postgres auto vacuum, which is very difficult to tune and a bit foreign, coming from operating MySQL for 10 years almost at Shopify and before that. But one of the companies, it's this company called Readwise, and what Readwise builds is an engine to help you read better. And they have articles, they have highlights from your articles and articles that books that you read from Kindle and things like that. And they wanted to do recommendations, or at least try it out, So we ran kind of a two-week sprint on doing recommendations. And so I was really interested in vectors because back at Shopify, I had worked a bit on search, mostly on the infrastructure side, but I mean, you end up working a bit of everything. And bringing relevant search results is kind of a nebulous activity, right? Of trying to, someone searches for red dress on an e-commerce store, and you need to show them a burgundy skirt because you don't have a red dress, but maybe they're interested in this. And so there's a lot of that. And taking strings of data and turning them into things, as we used to say, as my coworker Doug always said, we need to make strings into things, is very difficult when all you have are strings. And of course, vectors solve that problem. They take red dress and burgundy skirt and place them adjacent in a coordinate system. And we wanted to do that with articles, right? The LLMs, you basically chop the head off the LLM and out comes embeddings, because it's an internal representation that often these are trained on. You do some fine tuning specifically for this, but that's a simple way to think about it. And what we did was that we took these articles and then we built vector representations of them, and then thinking, okay, these articles that are going to be adjacent in vector space with a small distance between them in the coordinate system are going to be good recommendations. And we actually got pretty good recommendations out of it. They were okay, not phenomenal. This was early in the LLM and embedding days in 2022, but it was pretty good, and it was better than I could have done with strings. And then we ran the back of the envelope math on putting this on one of the vector search engines at the time. And it was a phenomenal cost, like around $30,000 a month for a company that was spending maybe $4,000 to $5,000 a month on their Postgres database. So it just seemed out of reach, and it was a sad event because we had this idea that actually worked, and we wanted it to come into the product, but cost was holding us back. And so I distinctly remember Dan, one of the co-founders, saying, well, I'm sure the costs are going to drop, just as they are for LLMs and costs. 4 or 5 months later, I couldn't stop thinking about this problem, and no one had come out with a vector search solution that was more economical, right? It was literally holding product back at this company. And I thought, well, there must be some latent demand here. There's this paradox. I think that's one more claim with AI and the reduction in price in AI, Jevons paradox, that basically says that if you make gas cheaper by, let's say, 20%, then people drive often more than 20% more, right? And you can intuit that this is as in, if you make gas cheaper, you live in Berlin, right? And there may be some trade route to some other city for some local company that's selling whatever pastry. And now they're going to start offering to also sell that in Hamburg because the fuel costs are now working out. And so the activity you get there, this is the same argument for making energy cheaper, is nonlinear. And so I thought that might be here for search engines, the way that it has been for analytical data in the 2010s. And I didn't see all this at the time, so there's a little bit of retroactive analysis here. But certainly I saw the example firsthand with Readwise. And so I thought that, thinking back on my experience at Shopify working on search, it was very clear to me that working on the Elastic clusters at Shopify was one of the hardest databases to operate, right? Fulfill the real function, and it was the best thing on the market, but it was a very difficult thing to upgrade, scale, and it was holding back a lot of search for a variety of reasons, cost being one, indexing performance being another. And I just thought back of the days that I've been debugging these clusters until midnight, trying to get them to perform better or some incident. And my experience at Readwise, and thinking that, okay, you know what, maybe things have transpired that it's time for a new search engine. And vectors seem to be pressing this even more, because vectors, when it comes to text, which is still the most ubiquitous form of data, when it comes to text, the vector representation of the text is often larger than the canonical text representation. You can imagine an article that's maybe 1,000 tokens long, right? So you represent that as 1,000 tokens. Maybe the tokens are 5 bytes on average, so that's about 5-6 kilobytes, right, of data for the raw text. Compresses incredibly well, right? So it's going to be hundreds of bytes to store this. Now, a vector representation of that text, you're going to have multiple vectors, maybe one per paragraph or something along those lines, not muddle the vector space too much. And so let's say that this 1,000 token article is now four vectors. And those vectors might all be 1536 dimensions. So that's around 6 kilobytes each. So now you have 4 times 6 kilobytes, right? So 24 kilobytes. And you can't really compress these vectors because they're every floating point has so much semantic information in them that you can't really compress them well like you can with text, where there's a lot of repeatability. And so now you've got this like vector representation that's almost 20 to 30 times larger than the compressed representation of the text itself. And that's why we saw in Readwise that the vector cost was so high, because all of it had to be stored in memory for a variety of reasons. And it was larger than all the origin data and the compressed representation inside of Postgres, where the article was also stored. And so that's always been a problem with search. It's always been expensive, because even inverted indexes also have this storage amplification, right? It stores how many bits do you store per bit of input data. And for an inverted index, that might be somewhere between 1.5 or 2.5. Sometimes it's smaller than even the origin text, depending, but it's generally in that range. But now we're talking about a storage amplification of 10, 30x, right? Which is far greater. So if you build a database on top of object storage, as we talked about in the other episode, the fundamental trade-offs are high write latency to write directly to object storage in the hundreds of milliseconds, and high tail latency in the hundreds of milliseconds when something is called on object storage. These seem like phenomenal trade-offs for search, especially if you then make it 100 times cheaper, which S3 is, right? 2 cents per gigabyte, and memory is around 2 cents per or $2 per gigabyte. That seems like a good trade-off. And the second search query, things are loaded into memory and things are going to be fast. So that is kind of the origin story of TurboPuffer.
Very interesting. So it looks like the cost was at the center of your decision making, right? Because that was the main problem, as you discussed, about like the storage amplification. And like apart from cost, of course, like we discussed in the last episode, like building something on top of S3, you already have a lot of guarantees around durability and the scalability of the system, so you don't have to build that into your system. Of course, you have to think about it and handle some of the edge cases, and as you said about latency, write latency and tail latency, but then that also simplifies your architecture, right? So You also mentioned about some of the terms, like you used term called embeddings. You use terms, I don't know, vectors and dimensions and tokens and stuff like that. So I don't want to assume that all our viewers know all these basics. So let's like quickly get these basics out of the picture so we can talk about the real stuff, like how it works. So what exactly is vector search? What exactly do we mean by embeddings? We can probably take an example and talk about it and explain in really simple terms what they mean.
Yeah. First off, I use vectors and embedding somewhat interchangeably. I think there might be a more precise definition for each, but for all intents and purposes, we can talk about them as the same.
Yeah.
Um, and what are they? Well, LLMs are very, very good at knowing what data is relevant to other data. That's why they're next token predictors, right? So, you have hello, and it thinks that there's a very high probability that the next word is going to be world. And that's fundamentally what an LLM is able to do. And one of the internal representation of that are a bunch of floating point numbers. And you could think about them in the simplest way that if you had a two-dimensional point and you trained a model to figure out that points that are close to each other in space are also semantically close to each other. So what I mean by that is that you take a banana and you take an apple and you train a model to say, well, they're pretty close. They're not quite the same. Like a pear is maybe closer to an apple than a banana, but they're pretty close. I mean, they're at least closer than computer is to any of those words. Well, now you end up with a coordinate system, right? And it's easiest to intuit this in two dimensions. So you end up with a coordinate system and you will end up with essentially these clusters, right? There's going to be a fruit cluster. There's going to be a electronics cluster. There's going to be a whatever animal cluster, whatever, right? So that information that is close in the coordinate system have coordinates or are also semantically close in the real world, right? So that's really what a vector or embedding is. It's that it's a point in a coordinate system where stuff that is related to other stuff is close, right? The easiest thing is just to think about the Euclidean distance between the 2 points. So
Yeah.
that's just what you did in, geometry in 6th grade or whatever, right? LLMs are very, very good at taking information and turning them into a bunch of a long floating point representation in this vector space. The reason we call it vector space and not a point is because it's not in 2 dimensions. It's in maybe some multiple of 64, 128, 384, whatever, often thousands of dimensions. And you can think about each of these dimensions maybe representing a real thing. We don't really know what they do, right? It's latent space. We don't completely know without spending a lot of effort on it. But you could imagine that maybe one of these dimensions, maybe the 0th dimension, represents something about size, right? So an elephant has a very high floating point number as the first one, and an ant has a very low number. Maybe dimension number 1 represents something about color, right? And represent the index number 2 something about like maybe where in the globe this thing is often presents itself, right?
Mm-hmm.
So you can imagine then you can represent almost every object like that, and that's what LLMs are very, very good at. So LLMs are good at taking information and turning them into a coordinate system into a point in a coordinate system. What we were not so good at was storing this coordinate system, right? And making it cheap to store and cheap to query. So it's been cheap to take information and turn it into a point in a coordinate system, but not so cheap to store to the coordinate system and ask it questions in high dimensional space of what's adjacent to this, what's close to this point, what's the average of something that's close to these points, or whatever questions you could think to ask such a coordinate system. And that's what the ANN, or the approximate nearest neighbor index, is, or is representing that coordinate system in a way that's efficient for querying.
Interesting. So I think, yeah, that's a very like clear example and clear picture of what all these things mean. Of course, there are so many dimensions to think about when we search about things, and not like a direct search but semantic searching. That sounds good. So let's take an example. So for our entire discussion, so we can base our discussion around that example and try to model that and solve that in a way using vector search and vector databases, and how we can do that. Let's say using TurboPuffer. So the example is again related to the podcast. So so far, let's say I have more than 100 episodes, and I want to kind of search across all the episodes that I have. Give me all the clips. So this is like the high level feature that I'm talking about, right? And then we can go a bit lower. Give me all the clips of discussions where we were talking about a certain database or a certain index, like binary search or something like that. Um, so given a specific topic, I want a clip, like timestamps of all the clips that I have, right? And specific to my podcast, for example. So if I have to build this, how do I start, thinking about this problem space? How do I know that vector search is something suitable here? Vector databases are something suitable here. And, let's start talking about that.
Yeah, absolutely. So I love rooting all of this is in an example, and I'll try to bring it back into the vocabulary we were using. So
Yeah.
let's design a search engine that searches through all this data so that if I search for object storage, right, this episode will come up, and the relevant points are going to come up when we talked about that in either episode. So the way you would do this, right, is that you have to make a decision of what's my chunk. It's called, right. Chunk is what information am I feeding into the model to get a point in the coordinate system, get the vector or the embedding. And we have to decide what that's going to be. So we could maybe take the entire episode and turn it into a point in the coordinate system. That might work, right? That's basically, can we fit the entire episode inside of a context window? But intuitively, it would be very difficult to represent an entire episode about a vector database in a, say, 1024 dimensional space, right? That's a very, very, very good compression algorithm if we're able to do that. So we might go a little bit lower granularity. That would be very cheap, right? Because you have 100 episodes, so 100 vectors, right? We're not talking about that much data, 6 kilobytes each, 100, right? So we're talking like less than a megabyte of data. So that would be great. It's very simple. We could just do that in memory in JavaScript in the browser. But the search is not going to be great. So if we break it down and trade a little bit more complexity here for a better search experience, we might say that we're going to chunk based on, let's say, every 30 seconds, right? So we say, okay, every 30 seconds, we're just going to do a hard cutoff and then create an embedding for that. And that's probably going to be a decent representation. Right. How far in the vector space, if you intuit it, how far in the vector space can you really make it and color the whole coordinate system in 30 seconds? So then we would take an episode like this, right? And let's say it's 60 minutes, then you're going to have 120 embeddings. Still a very manageable amount of time of data, right? So 120 times 100 episodes times 20, like 1024 dimensions. And let's say we're storing it all as 4-byte integers. That's like 50 megabytes of data. So we could, again, it's like manageable in memory or something like that. So it's a very manageable amount of data. We could build probably a pretty good search engine on that. If you ship that, you could ship that on TurboPuffer. But frankly, with that few vectors, you could also do it in memory. Like you can search a 50 megabytes very fast, right? We can search memory at this point at 20 to 30 gigabits per second on a fairly small machine. So you could do that. And we would get pretty good search results. And at this point, we could start to, again, ratchet up complexity for a better experience. So one way that we could improve the performance then is that right now, the default way is that you take the query might be TurboPuffer, and we search for TurboPuffer, and then we turn that into an embedding, and then we do the query to the coordinate system. In this case, we might just exhaustively search through all the vectors of all the episodes and then return the top results. And for 50 megabytes, we might be able to do that in tens of milliseconds on a small machine. So it's not too bad.
Yeah.
If we had 10x that amount of data, like 500 megabytes, we're starting to run into latency on this, especially as we get into gigabytes. But it would work. It would just be slower.
Yeah.
So what you can then do for that is you can build an approximate neighbor index. It's called ANN. What we're doing there is we're doing a KNN search. So we're searching for the vector over ON of all the other vectors and finding the top 10 results to show on a search page. An approximate nearest neighbor index is one where we trade off a little bit of precision or recall, it's called, by building an approximate kind of geometric index of this representation. So one way you can do it, the simplest way to do it, is that you take all the data and you try to cluster it. So you take every point and you try to see, okay, in this conversation, right, we're talking a bit about databases, we're talking a bit about vectors, we're talking a bit about Shopify, we're talking about this and that, and some clusters of conversation might emerge, right?
Mhm.
So these 30-second clips can now be set into these clusters. To make the search faster, we could imagine that you search for TurboPuffer and it looks for a cluster maybe on databases based on this conversation, and it searches only that cluster. It's not searching the Shopify cluster. It's not searching the whatever. Well, I mean, we're going to talk about databases the whole time, so it might be like there might be some sub clusters in that cluster.
Yeah.
But intuitively, you can imagine there's a banana cluster, right? There's an animal cluster, and there's a computer cluster, right? And you only search the relevant one. And that clustering you do with an algorithm, you use something called k-means, right? That sort of groups content together. To do it optimally is kind of an NP-complete problem. So you have to do some approximation. Now, this is not always going to work, right? You're going to search for something that straddles the boundary between some of these representations. If you're searching in music, there may be artists that are not pop, not rock, but they're somewhere in between. And so there's some approximation with how many clusters you visit, right? So you can imagine that you might have a vector index with 1 million vectors, and you might have, let's say, 1,000 of these centroids, right? These clusters that in the content. And you have to choose how many clusters that are adjacent, that are closest to your query vector, you're going to look at. And so that's one of your trade-offs in these approximate nearest neighbor indexes. There's also other ways to, there's other data structures that you can use to represent it, but this is this is probably the simplest one. So we could do that to speed up the search, right, for your podcast search website. The other thing we can do is we can try to improve the search results. So what we might find maybe is that the 30-second boundary is not great. It doesn't represent itself well. Sometimes we're changing topics a lot. So you might try to kind of find a way to represent an embedding that is sort of at some normal conversational margin. You know, this is a podcast, so you're kind of asking me questions, and then I might give embarrassingly long answers. But this is not you can't embed all of that because I'll change what I'm talking about all the time. So you might maybe use an LLM, maybe a very fast, cheap LLM, to figure out what the boundaries are and then do embeddings on that. Maybe you find another way. Maybe you're always doing it based on sentence. Like there could be all kinds of ways of deciding what the embedding should be to improve the relevance. Another thing you could do is that you could try to incorporate other ranking signals to improve the relevance, right? So you could do things like, I'm going to weight podcasts that are more recent higher. You might do that. You might also combine it with a text index, because maybe the embedding model doesn't have any chance to know what TurboPuffer is. And so it thinks that TurboPuffer is maybe a fast fish, but really it should be categorized in the database cluster, and you might get bad results as a result of that. So then full text search is going to be great because it will know to just match directly on TurboPuffer, and maybe we give that a higher relevance. So this is kind of the curse of search, is that iterative loop of, okay, are my improving search results? You have some test cases, you look at whether they're better against what you would know, what you would do knowing all the data. So this is kind of like that constant push and pull between, am I going to put more data in the database, and how do I index it faster? That's the part that something like TurboPuffer takes care of. And then you take care of knowing your data, your users, how you want your search to be structured, of improving all these different signals via the APIs that TurboPuffer or another vector database or search engine in general you're using. So we don't think of TurboPuffer as just a vector database. It's certainly like a prominent feature, and we're very good at storing vectors. But we can also do full text search and other things to help you get good search results.
Okay. I think that's a good mental model, like how we should start thinking about the problem, and when we really face that kind of problem. For example, for this kind of data, I don't think that we really need a database, as you said. We can also do it in memory, right? But then you have to also keep tuning about the search results and how many how you are planning to do the the chunking, and probably you want to create more clusters, then you can think about making it faster and so on. So I think this example, if we start thinking about a pretty high scale. For example, let's say this now I want to build as a service, like for all the podcasters, right? And I want to onboard them. So this massively increases the scale, and there are many other things coming into the picture. Because the data size increases, the type of podcast and the discussions would increase, not only technology, but maybe something else as well. So I think uh, depending on how you want to provide the search, how you want to chunk the episodes, how you want to add more clusters. I think that all adds up to the complexity and the solution we should be aiming for, right? Like maybe for this podcast, it's fine to just do it in memory. But maybe if we do it for all the podcasts, right, we want to like have many more podcasters on this platform, then it becomes a big problem, right? And something where we need to focus on also on cost effectiveness and stuff like that.
That's right.
So there are so
One
many. Yeah.
one thing there, just before we move on, is that you might decide to use a search engine even if you have a small amount of data,
Mhm.
just because it provides the APIs to do some of these other things like full text search. You don't have to do all these things in memory.
Right.
So that would be one reason. And I mean, if you only have a couple hundred vectors, TurboPuffer also just exhaustively searches. We don't index it at all.
Right.
Sorry, go on.
No, I think that makes sense. So I think the decision has to be based not only on the cost aspect, not only on what you want to provide, but maybe if the some database provides you a simple solution, just using that and getting a mix of vector search and full text search, I think that could also help. But as you said, let's increase the scale of the problem, right? Like there are so many podcasts, many types of topics, different lengths, different guests. Probably there are also like specific guests that people want to search on, right? For example, if I have like group discussion, right, not just one-on-one, but maybe there are more people in the discussion. So people would also want to search when when Simon talked about this thing, right? So that adds up to the type of clusters we want to create and the index that would work on. So let's increase the scale of the problem, increase the variety of the data, and then start thinking about uh, the problems that I might get when the latency spikes or the size of the data grows and the cost increases. So how should I think about that?
Cool. We can walk up the order of magnitudes here. I think that's an interesting exercise. So yeah, at like let's say at the 50 megabytes, which would probably what the vector representation here would be. First of all, that's much more than the text, right, of all of this, right, which should
Right.
compress well. So yeah, if you go up in complexity and you start to search more data, you might have millions or in the millions of vector. Most databases can do a really good job of vector search, right?
Mm.
So if you have a Postgres instance, Postgres comes with a number of different extensions that you can find that are open source to do vector indexing. And honestly, that's great. If you just have a couple million vectors and the features in Postgres are going to get you there from a relevance point of view, that's probably simpler than introducing something else that you have to replicate data into. Where we start to see our customers seeking us out is when you start to get into the tens of million or even into the hundreds of million. That's when building these indexes and storing all the data and querying it, especially if you're doing it with a where clause, starts to get tricky. Let's talk about the where clause for a second, because you asked about that of, well, what if I want to search for a particular author,
Mm.
or maybe I want to search for a particular date range, or I want to search for a language. Well, now your vector space is not just what's the closest thing. It's what's the closest thing that also matches this filter. So it's not just about what's similar, but what's similar that also has this hard constraint.
Mm.
That starts to get very tricky. We have a blog post on our website where we talk about what we do here. But at a high level, you can think about it as, let's say that we've tuned this to know that when I search for something, I look at the 3 closest clusters and I search for everything that's in those clusters. So by default, let's say that those clusters are of size 1,000. I'm just making up numbers here, right? So that means that every time we search something, we're looking at around 3,000 vectors to try to get a good accurate result, right? For KNN, we search at everything, so we know that that's 100% accurate. And for an ANN index, often they're 95 or so percent accurate or more, which means that for say the top 10 results that you get from an exact search and the top 10 results you get from the approximate index, 95% of the time, basically there's an overlap. Actually, yeah, on average, right, across everything. So some are going to be 80, some are going to be 100.
Yeah.
So that's what recall means in that context, and that's a very important thing for any vector database. And when you have a where clause, maintaining high recall of 95% starts to get more tricky. Because imagine now I search for those 3 clusters, and they have 1,000 vectors each, but only 500 of those vectors match the filter. Well, now I'm only looking at 1,500 vectors every time I do a search query. Is that really enough to get 95% recall? Generally not. You probably want to still look at 3,000 as you were in the other case. So now I have to look at more clusters, and I have to keep looking at clusters until I've looked at maybe 3,000 vectors. These are the things that make ANN indexing very tricky, because you have to tune this for the data set, and you have to tune this for basically like how rare is the filter. This one was one that cut 50% off. But if you cut 90% off, maybe you have to look at more clusters, or maybe you can come up with another clever way of navigating the clusters. Maybe you have another index where you execute the where clause, and then you just look up the clusters and know how much matches. So there's lots of different ways that the query planner here has to take into account to provide high recall with the filtering. That's the kind of stuff that we talk about when we talk about vector databases and why a new category emerged. I think that category will turn from vector databases into search engines. But this is the kind of thing that sometimes Postgres will have trouble with. Postgres will make some naive decision and not have a query planner that's completely integrated into the high recall use case. So we see some cases of this. You can get away with this by just looking at more data or pre-filtering and things like that. But in general, this starts to be challenging. The other thing that gets challenging, and when you get into the tens of million or hundreds of million of vectors, is that the vectors are large and do not compress well. If you store it in Postgres, right, you are kind of by definition in a relational database, you're going to store it on the writer, so the main replica, and then you will often store it on 2 replicas, right, in the 2 read replicas off of the writer. So this means that you're storing the data 3 times. The other thing you're going to do is that no one in their right mind is going to run a database at a 90% disk utilization, right? That's just too scary. Yeah. So you might run it at, let's say, 50% you might be comfortable with. So now we have to buy the actual disk to store the data on. And those disks, like let's say an EBS volume or a PD in GCP, cost you somewhere between 10 and 20 cents per gigabyte, depending on what's underlying this disk. NVMe is a little cheaper, maybe 8 cents, but it has its own challenges because as soon as you restart the node, it's gone. So you really want to know what you're doing before going to those. So with the network disks, 10 cents per gigabyte. Let's say, let's round down to that. But because it's 50% disk utilization, you're actually paying 20, and you have 3 of them. So this means that every gigabyte of data you store, you have to pay for it 3 times, and then you have to multiply by 2 because of disk utilization. So you're paying 60 cents per gigabyte of data stored. On object storage, you pay 2 cents per gigabyte. Of course, with vectors too, you're not just storing the vector once. You often store the vector multiple times. You have to do all these things where sometimes you store it not just in the cluster closest, but in multiple clusters and things like that. So it's often these indexes get even larger than just storing the vector multiple times, which is why something like Postgres and the economics of it start to at some point not make sense. So at some point, essentially, if you think about 2 things to optimize for is the cost and operational complexity, and then the cost and then the operational complexity of having a different database. At some point, those graphs cross, and you may decide that you want to abstract it out. Since the dawn of time, something like Postgres has had full text search features. MySQL has had Sphinx and others. But often as companies scale, this becomes one of the things that gets uneconomical and it becomes difficult to manage inside the main database. Keep it in there for as long as you can because it's simple to manage. But there comes a point where babysitting that becomes more difficult than operating a separate search engine outside of the Postgres universe. And you might also be ready for some of the features to enhance your search that are not in there. So then it becomes a question of that and also of indexing, right? Building an approximate nearest neighbor index is an expensive activity. If you have a 32 core Postgres cluster, a 64 core cluster, and you're building a 100 million index, that could consume all of your CPUs while you're doing that. I love the DBAs at Shopify, but I don't think any of them would let me run ANN on all of those hundreds of thousands of shards, right? To build ANN indexes at that scale. So that's kind of the trade-off, right? But I would encourage people to use, like, if they can get away with the features inside of something like Postgres, I would really, really encourage it. And those are expanding over time. But you can't really outrun the economics. And they catch up to you quick because the vectors are so large.
Yeah, that's interesting, and I think it also adds up because let's say you use Postgres and you release a feature that, oh, now you can do this, but then you always want more features, right? Like more, your users want more features, and they want to search more, they want to also filter more, and then it's always going to grow. So even if it works now, maybe it won't work, let's say, in 6 months or 1 year down the line, depending on the data size, of course. So you mentioned a few interesting things there, like uh, one, like building these indexes is really expensive operation. So I want to understand how that is done. But before we do that, let's say now I decide to use like a vector database, and something like TurboPuffer, for example. When so I use a LLM, I create all the embeddings, and I give it to the like TurboPuffer. What exactly happens then? Like, when is the index created? Um, and the other question I wanted to ask was about recall, but probably after this question.
Yeah, I mean, simplified, when you write a vector to TurboPuffer, we put a file into object storage in our write-ahead log, right? Every new entry makes it in there.
Yeah,
And then we return an OK once we've committed to object storage. That's our fsync.
right.
And if you've committed 10 vectors into a TurboPuffer database, we call these namespaces. You can think about them as just a prefix on S3. When
Mhm.
you have written, say, 10 vectors and you query it, we're just going to load them all into memory, right? Like, or stream them in from S3, then into the disk cache and into memory, and then just exhaustively walk through them in a for loop, because that's just cheaper than doing anything else. Write 100 vectors, we'll still exhaustively search it. At 1,000, we'll probably still exhaustively search it. But once you get into many thousands or tens of thousands, then we'll start building the index. So the indexing nodes are going to get a notification to take that namespace, that prefix on S3. So let's say it's podcast slash, and it will go get podcast slash, and then it will start building the ANN index, right? If you're using a graph-based algorithm to do one thing, on TurboPuffer, it's always going to be something centroid or cluster-based, like I described before. There's a lot more tricks to it, but that's the indexing we'll do, and then we'll start building that index. So when you then query TurboPuffer, it will look for inside of that prefix whether there's, let's say, an index file, and if there's an index file, then it will go and look up the vector in the index. If not, it will just exhaustively search and apply the newest wall on top of the index for that namespace. Yeah, that's how the writes work.
Interesting. So it automatically decides that, oh, this is the right time I should build indexes, because the data is growing, and the user doesn't have to do anything about, oh, create index, something like that. So that's not there. It automatically decides. And then on the query side, if, like, how does it know that for this particular query using an index would be better? Because that may also depend on the query itself, right?
Yeah, so that's the query planner's job, right? By default, with ANN searches, it will always use the index if it's there. How exactly it uses the index, and I mean, there's multiple indexes, right? If you're filtering, then we have to build non-ANN indexes for that and kind of interleave them. The query planner has to look at the statistics of the data distribution and make decisions about how it's going to do that to provide high recall for the query. But if there's an index, we'll always use the index.
Okay, interesting. And what are the other types of indexes that are typically useful? And how does it decide, like based on the nature of the data or the queries it has seen, or how does it like decide what kind of index would be suitable, or maybe multiple indexes, and the query planner can decide, oh, use this index and use that.
There's multiple types of ANN. Again, these are the approximate neighbor indexes that are in use today in production. I'd say in broad strokes, there are two that are most used. There are the centroid-based ones. That's what TurboPuffer uses because it works best for object storage and it works really well for lots of writes for reasons we can get into if you want to get into that. And then there are the graph-based indexes. The graph-based indexes are phenomenally fast at queries, right? So where a centroid-based index might take a millisecond, a graph-based index might take 100 microseconds, right? But everything has to be generally in memory for a graph-based index. So that's the downside. So if you're doing 100,000 queries per node per second and you want to do it in a single node, it's very hard to beat a graph index. But very few people are doing that. So that's why we think the centroid-based approach is very, very good for a lot of workloads. The graph-based indexes, if we just get into it a little bit, a graph-based index, you can imagine as you try to build a graph over time where vectors that are close in vector space are also connected in the graph. Then essentially you can imagine that you start in the middle of the graph and then you look at, okay, this graph might have, like say 64 other nodes or vectors that it's connected to. I'm going to go and look at the one that I'm closest to and perform a greedy search. Then I have a priority queue of what am I now closest to, and I keep navigating the graph for some hyperparameter tuned like number of steps and size of the priority queue. And then at some point I spit out the result. This is really fast in memory. But the trade-off is that when you navigate a graph, you have to do a lot of round trips, right? So it's like I go here, then I have to go get this data. Then I go to the next point in the graph, then the next point in the graph. And every time I do that, I have to do a round trip. A round trip to memory is fast, right? It's in low hundreds of nanoseconds. And if it's in the CPU cache, it's in single digit nanosecond. It's very fast to do 10 or 20 of them. But if you're going to a disk, a random read to an SSD could easily be in single digit milliseconds, even for an NVMe SSD. And for object storage, of course, we're talking hundreds of milliseconds for every round trip. So the way that something like TurboPuffer is designed, it just doesn't fundamentally work well with a graph. You can do things with a graph to shrink what's called the diameter of the graph to try to minimize the number of jumps you have to do, but you start to lose a lot of the benefits of it being a graph to begin with. So the centroid-based approach, right? We're back to the coordinate system. We're back to finding information that semantically groups in clusters, right? We have the rock cluster, the pop cluster, and the electronics cluster, right? So data that naturally groups together will also naturally work when we then search for, electronic dance music, and then it goes to the electronic cluster and searches just that. So centroid-based indexes make use of that. And they work really well for object storage because we just have to do fundamentally 2 round trips, right? We have to store all the centroids somewhere. The centroids are the average of all the vectors in the cluster. And we just search all of those. We find the top K closest cluster, and then we go download all those clusters. So we're downloading a lot more data than we do in the graph, but that's what disks and S3 is very, very good at, is downloading a lot of data. This is also called IO depth, right? Like basically this fan out can be very, very high. But if you have everything in memory, fundamentally it could be a bit slower than doing a bunch of round trips, right? Which is the fundamental trade-off between these two approaches. But it works very, very well for object storage and for disk to do this centroid-based approach.
Interesting. And do you also do this like in parallel? For example, so I imagine that when you say, okay, search this cluster and the other cluster, these are again S3 files, right? And so if you have to search, like let's say a given search space, you already know that. So you could also make parallel calls to the S3 and make the search results be faster, right?
Of course. Yeah, we do exactly that. I mean, we go way beyond that, right? And when when we search for something, we do all these S3 requests. But even the S3 request, often you want to, if a block is larger than 4 megabytes, you want to do multiple block fetches and things like that. So there's lots of optimizations you can do to try to saturate the network. When the bits come back on the wire from S3, we just like transpose it, project it directly into memory. It's completely zero copy, right? So we can get it as fast as possible with as few memory copies as possible. So the only copy should be the copy from the network buffer right into userland, which with IOU ring and so on, you can even get around that. So that is exactly like that massive concurrency is really good for S3. And it happens to be also very good for modern disks. A lot of software today, including all the Unix utilities like tar and so on, do not take advantage of the fact that you can do so many concurrent reads to a disk, a ridiculous amount, right? Millions per second. And very little software today takes advantage of that. You have to remember that these kinds of SSDs only became generally available in AWS in mid-2018. Not a lot of databases take full advantage of something that was only GA in the clouds that late.
Interesting. That's very interesting. The other thing that you mentioned, and I want to understand how that would work, is so basically you may end up searching everything, or you may end up searching parts of the cluster depending on if you already have the index. And you use a term called recall, right? So you also want to meet a certain level, let's say 95%, right? How do you compare? How do you measure that the recall is not going down? And where is that happening?
So there's two ways of doing it. There is the like academic way or the CI way, where you generate a bunch of data sets and then you generate a bunch of queries. And for every query, you do KNN search, so the exact search, right? The 100% accuracy search that's slow. And you generate the correct result for, let's say, the top 10.
Yeah.
And then you run your approximate queries, and then you compare the result, and you see, okay, it's on this query, it's 90% match. On this one, it's 80. On this one, it's 100. You average the results, you got the recall. That is every vendor does that, right? Everyone runs that as part of their CI, or when they make changes to how their ANN indexing works, they run this on a bunch of different benchmarks. So that's table stakes. If you can go beyond that and generate your own data sets, you can do it with filtering, right? Which is the difficult thing. It's not that hard to do ANN search, but it's harder to do ANN search with where conditions and filters. Then you need data sets around that. Make sure that the recall is high for that. Again, you can do it against an exhaustive search. So that's the one way. We do that. Of course we do. But we are also very humble to the challenge of production, where we don't control the data distributions. Academic data sets tend to have nice data distributions and not always have the like messiness of real world, where you might have like a million duplicates and things like that, and you still need high recall. And what we do is that in production, for a percentage of queries, we run recall in production. So we have a fleet of nodes, and all they do is just run exhaustive searches against ANN queries to see what the actual recall is. And inside of our Datadog, we then have grouped by all the different organizations. We can see what their actual in production recall is, so that when we tune the indexes and ship changes to make sure that this is meeting a high quality bar. But recall is very tricky to get right on every single query, which is why we do this empirically. You can imagine that there's some data sets, for example, where this is something we come up against a lot, where we run a POC with a customer, we share the recall numbers, and maybe the recall is, let's say, 92%. They're like, oh, we want it to be like 98%. We look at the queries, and it might be that they have a lot of queries that don't have a good result. If you search for text, if you search for TurboPuffer in a data set that doesn't mention TurboPuffer, you will just get 0 results, and you will be happy with that, because there is nothing about this thing. Even if there is something about vector databases, or if there is something about fast fish, you're just not going to get it, right? And that's fine, right? We've reached the limits of full text search. But for vectors, there is no such thing as a 0 result, right?
Yeah.
A banana is similar to a computer in some way. I mean, an apple is maybe more related to a computer than a banana is, but they're related in some way. So when we analyze recall on some of our customers' data sets, often it's because they do what it would be traditionally be a zero result. But because everything is related to everything else in vector space, there's no such thing as a zero result. And you can intuit that if you search for something in a coordinate system and nothing is close to it, and all the clusters are really far away, it sort of ends up being a bit randomized what results you get, especially in a centroid-based approach. In a graph approach, often it fares better on these results that don't matter, but on a centroid approach, not so much. So we see a lot of also limitations of recall in that way as a general measure. It's a really useful signal, but there are cases where it doesn't fare that well because it doesn't encapsulate this kind of thing in real life. We would never have, we don't see this in academic data sets because often, not in all of them anyway, but in a lot of the academic data sets, they do have good like query distribution against the actual data. But in real life data sets, people will search for things that are not even close to what's in the data set.
Interesting. Yeah, that's a very good point. And of course, it's very challenging, right? Like to observe this thing, and you cannot probably do it on each query. Talking about going a bit further into the database, right? Like you said, you have S3 files, and I if I remember correctly, last time we discussed about the particular format that you use, and I think you use the library called archive for the storage format. Is it the same format that you have for indexes and the data, or is it something different?
I mean, we do intentionally have some differences in how we store in the index and the data. Part of that is just safety, right? Like it's like it's if God forbid we caused a problem in how the data is indexed, well then we have it in different code path for the where it's written into the wall. So it's a safety thing that they are similar. But they both use archive, and of course there's overlapping. There's some overlap in how we do it, but it's both archive. RKYV is a Rust project that allows you to write zero copy Rust data storage formats.
Interesting. Cool. Talking about like so we discussed like how the data is getting ingested, how files are getting created in S3, and then how indexes and when indexes are going to be created. What does it give me back? Like, is it again like a set of vectors, or because whatever I am ingesting in the database is basically only embeddings, right? How do I convert back the embeddings into something meaningful?
Yeah, so generally what you do, right, is that if you have a chunk of text, again, a snippet of a podcast episode in raw text, you send that to OpenAI or Voyager or Gina or one of these companies that specialize in creating embeddings and training models for it, and you get back the vector, right, to a bunch of floating point numbers. Typically what we see our customers do is that they will send the raw text alongside, or the raw image or whatever the raw entity is, alongside the text. Because we store it on object storage, you can then say, well, I don't need filtering on this, I just need it to be stored alongside. We can give you a heavy discount because it's stored inside a TurboPuffer on object storage like that. So generally, you don't try to reverse engineer it. You just store the canonical data, and there's inevitably going to be some loss of precision where you can't. I mean, it would be a little bit like taking like a JPEG, downscaling it, and then expecting it to be able to upscale it again, right? You are compressing it in some way, even though it is often larger than the origin text, right? For images, often it's smaller, but for something like text, it's generally bigger. But it's lossy compression.
Okay. So what I get back is already the original data, right? Because you're storing it closer in the vector database.
Yeah, alongside the vector, yeah.
Okay, so that's really powerful. Also, in case of TurboPuffer, because anyway the storage is all in object storage. So even if I give the entire data there, the size of the data is not going to increase the cost, because I also have the data and I also have the embeddings and stuff like that. Of course, the data doesn't grow with the type of queries that you're doing, like the number of vectors you're going to create and so on. So I think the data is still lower as compared to the vector and the indexes that you're storing, right?
Generally, yes, right?
Okay.
There's edge cases to everything. You could do embeddings of massive pieces of text, but in general, yes, exactly.
Interesting. That's cool. What are like some of the interesting use cases that you have seen? People using TurboPuffer and using it for like a combination of vector search and full text search. And what are some of the challenges that you have seen?
Yeah. So we can talk about through some of the case studies of some of our customers, right? So we've got Cursor is one of our customers, and Cursor, of course, if you use Cursor, you'll have see that sometimes it draws context in from the code base. So you might search for the LLM might try to search for the code that does the clustering, and then it knows that, oh, it's the k-means code. It's in this file that we don't have open right now. So that's what Cursor can use to have the agents and the edits and things like that, draw in context from the entire code base. So that's one way that they use it. They trained their own embedding model, where they take the code and they chunk it up and then encode it with their own embedding model. That Aman, one of the co-founders, tweeted some really impressive stats about this embedding model that they trained. So that's one use case. Another use case is Cursor, or sorry, Notion. So Notion, if you're inside of Notion, you have the ability to use AI to start documents, ask it questions about your data. What's my company's leave policy, whatever it might be, or you might be, hey, can you draft a document about this for our weekly meeting? And from that, it needs to draw in context from your Notion workspace, and so they can create embeddings of all of your entire Notion workspace, and then sort them in TurboPuffer, and then enhance the LLM to that, right? So those would be some of the case studies of some of our customers, that people might know.
Yeah, absolutely. Like I think everyone might have used Cursor by now because it's so popular, and of course Notion as well. While I was thinking about like Notion and also some of the use cases, I don't know, for Canva, there's a lot of duplication, right? Like the people are creating same type of images and same type of videos and stuff like that. So do databases like TurboPuffer also take care of that to optimize that, like reducing the redundancy or the duplication, at least for the same customers, right? Maybe for different customers, you may not be able to do that, but for the same customers. So is it also done?
I mean, there's two answers to that question. I think that if you know that you have a lot of duplicates, then you can work on it on your data, right? You can represent a document that says, okay, this is the image, and here are all the places that it occurs in the data set, and do your own deduplication. So that would
Hmm.
be the customer doing it. If you have an image in, let's say, 100 Notion docs, we can't really know that. I mean, all those vectors are going to have different metadata, right? One is going to say, oh, I'm inside of this document and I'm inside of this document. So we can't really do much there. We
Right.
might be able to do something in the AN index where we compress it harder because we know the vectors are the same and they have these attributes. Those are the kinds of optimizations that a good AN index will do when it encounters a lot of duplicate data. But it can be hard to generically do it across all attributes, right? But generally, TurboPuffer is at a price point where we don't really want people to have to worry about these things, right?
Right.
We want people to just pump in a lot of data and all the data they can possibly get their hands off and make it available to the LLM that they want to query, whether it's through an agent, Q&A, or just general search for the end user. So we don't want people to have to worry too much about that kind of thing.
That's fair enough, right? Because ultimately the cost of data is what you are optimized on. So people may not have to worry about that. And how do you make sure that since these like creation of indexes and I don't know, even search, it's a pretty expensive operation, like you're doing. How do you make sure that the different tenants or like customers are have enough isolation so they don't have problems, especially when you have things on object storage?
Yeah, so object storage is by nature very good at multi-tenancy, right? There's
Hmm.
certain things that you do on object storage to make it better at multi-tenancy. One of those things, for example, is that at the end of the day, what object storage does is that, like most pretty much every database does some kind of sharding. It's just a question of whether it's automatic or not.
Yeah.
And S3 and Google Cloud Storage and Azure and all of them do the same thing where, if you have three keys, A, B, and C, and A and B are really, or like C is really, really hot and A and B are moderately hot, then it might decide to put A and B on some nodes and C on some other nodes, right? And continuously split the key space. So you can do various things to randomize the key space as much as possible so that this kind of activity gets better and everything gets uniformly over the shards. But in general, S3 is very good at this kind of stuff. GCS is very good at this kind of stuff. And we just have to help it a little bit. On our side, right, of course, when you query TurboPuffer, you will get into a node that we think has cache affinity to that data. And those nodes could get hot. And so there's various things we can do there to split traffic across multiple nodes. We can make sure that tenants aren't impeding on each other by limiting the amount of CPU for different tenants. So there's lots of different things like that you have to do when you run a multi-tenancy system. But the flexibility of this is great because suddenly you're ingesting 1 billion vectors in the course of over a few hours. We can scale that up, and we all share the compute when there's large spikes. So it works really well. And this is one of the things my co-founder Justin and I spend an enormous amount of time on at Shopify, which is probably one of the largest multi-tenancy systems in the world, right? It's making sure the capacity is fairly shared. Make sure that if one tenant drives millions of requests per second, which might often be bots, that other tenants do not get booted out or have some kind of degradation of service because of them. Prioritizing traffic for a tenant. So for example, traffic that has a cart is more valuable than traffic that doesn't, or whatever it might be. And we can do these kinds of things over time too, to make multi-tenancy really good for TurboPuffer. At the end of the day, multi-tenancy really, like the main thing you can do is just scale up as much as possible. And TurboPuffer can scale up very, very quickly. But at the end of the day, the clouds will only give you a machine in around 120 seconds or so before it's booted up, and TurboPuffer can bootstrap very quickly. So these are things that we'll get better at over time, but the system performs very, very well.
Very interesting. Talking about the observability, right? Like any database need to have some metrics around, how it is performing, query latencies, and index usage and stuff like that. What are some of the interesting metrics that are probably specific to vector searches and full text searches?
Sorry, for
understanding the performance and if there is any problem going on and if you need to scale up and stuff like that.
Sure. I mean, the biggest thing we look at is latency, right? So we look at query latency. You look at indexing throughput. So how many tens or hundreds of megabytes per second can you index? You look at how long the cache is living, right? How many days is something take until the TTL's out of the cache? We look at like raw throughput. We look at, you look at CPU and things like that. Of course, you look at memory, very standard things. I think maybe the most domain specific are just, what's the indexing throughput and how are we keeping up with how fast people are ingesting? So writing into the system, how fast are we indexing what people are ingesting? We can index at often up to tens of thousands of vectors per second. So as long as you're ingesting at a lower rate than that, we're good. If you are, we allow spikes and bursts, and maybe we'll throttle you worst case if we can't keep up. So these are the kinds of things that we look at on the right side. And on the query side, we have lots of tracing in place to look at query latencies and things like that. There's cold queries, there's warm queries, right? So we optimize both the cold queries coming straight out of object storage. We optimize the warm latency of those that are making it to NVMe SSDs, which takes quite a bit of work to make work really well. And then you optimize the hot queries in memory that are often quite fast.
Very cool. Where is this so I understand that more and more databases, because of cost reasons and because of all the simplicity that it brings in, people are moving to object storage, at least, right? In some of the use cases. Where do you see this, the trend of vector search and vector databases are going? And where do you see where TurboPuffer will be used more and more?
Yeah, I think what we see our customers doing is that they want to vectorize all the data they have, and they often have a lot more data than they're currently vectorizing. And so that's the number one. The second is that we see them wanting to do full text search, right? If you're searching in a data set, then the embedding model might not know all the terms, right? I'm sure you may use terms with your friends or family or your partner that an embedding model has no chance of knowing what they mean, right? And that's where full text search is really useful. If you're searching for an LG TV SKU, which is always some like weird combination of characters, full text search performs really well for that. So we see the vector databases, and at least ours, more from being primarily focused on vectors to being focused on search in general, right? And allowing you to rank, even if you're just doing vector search, a file that you just edited, or a document you just edited, or a song you just listened to, or whatever, might be more relevant. And so we have to help you with that kind of stuff. Typically, when you search, you sort of like take millions or tens of millions or billions of things and comb them down to a couple hundred. That's what TurboPuffer is good at. And once you have a couple of tens or hundreds of things, then typically you'll have a model where you give it the entire document or song. In your case, it would be the just that snippet of text and the query, and you kind of run the full LLM over it. You can imagine passing that to ChatGPT and then asking, what is the most relevant of these 10? And then you get a result back. And we see our role in that to do that first stage retrieval, right? To find not the needle in the haystack, but find the needles in the haystack that are relevant to you. And then it's your job to do the final ranking with some kind of like higher fidelity model. Could be an LLM, could be a trained re-ranker or something along those lines. So we see the trend here being that in the past, people are used to writing a giant JSON document to describe exactly how everything is ranked. We see that people are now writing, instead of writing big JSON queries or SQL queries, they're writing a simple JSON query or a simple SQL query to go from to go and locate the hundred or tens of needles in the haystack. And then in their Python script, use some kind of re-ranker. It's called a cross encoder or something else, based on these documents you get back. And this is very, very competitive to these very large JSON queries that we've seen in the past, passing into often these Lucene-based engines.
Very interesting. Cool. I think, in this 1 hour, we can only cover so much. So, but I think we have covered the basics and also some interesting things about how TurboPuffer is able to provide these features and how is it, cost effective and what are the challenges involved. But the space is large, right? What would you recommend people, read more in terms of, understanding vectors and, how they can build applications around search as a unified experience, not only vector, but maybe also full text and, exact searching and stuff like that. So are there any resources you would recommend?
Yeah, I mean, there's a lot of papers on all these indexing algorithms. I think that honestly, ChatGPT is pretty phenomenal for this kind of stuff. So I would ask it like, how does it work? What's a
Yeah.
graph-based index? What's a cluster-based index? Hey, can you please give me a super simple Python or JavaScript implementation? Play around with it. That's probably the most effective way if you have the patience to sit down with that. Our blog has some content. We would like more content, and docs have content on how these things work, how TurboPuffer work, the architecture of TurboPuffer. And I think that will be a good guide as well. For full text search, I mean, the Lucene source code is where I've learned almost everything that I know about this from. The docs are also quite good. I would recommend that you read the docs on how the data is stored. That's probably the most useful. And then if there's something you don't understand, get ChatGPT to reason through it with you. Probably Cursor on the Lucene code base is going to be hard to beat for learning how full text search works. There are books and things like that, but I think that actually going to the database with an inquisitive mind and some good questions, and just reading the source code and quizzing it is going to be the most effective way to learn as much as possible about this. The other thing I'll say is like to actually write the search application. That would be the first place that I would start, because you're going to just ask better questions as a result. So build the thing that you're building, right? Maybe someone should build that over your data set and hand you the keys. That is going to be the most useful way to have the best questions to ask once you want to learn. So I would always start with the actual use case.
Right. Awesome. Well, Simon, thanks a lot for joining me today and, sharing all the insights on how things are working in TurboPuffer. And I'll attach the links to the blog and, the interesting things that you mentioned. And so people can also refer and, but as you said, like building a search application and, solving a use case is going to be the best use of time and, learning reasoning with ChatGPT or something like that. That's going to be really powerful.
Absolutely. Thank you so
Awesome.
much for having me.
Absolutely. Pleasure.